Transformation of quadratic functions. All right, guys. Be sure to do the, oops, wrong. Is that the right one? No, actually, yes, it is. All right, guys, here's the lesson. As usual, make sure that you're copying down the underlined ones. So we're going to talk about the transformation of quadratic functions. This is no different from what we've done in the past. Remember, A, and I had used D in the past, right? A and D represents the vertical because that is something that you do to a function once you have a value of the function, right? So it affects the verticals. And the B and the H, and it was called C before, BC, AD versus BC, right? So it affects the X values, hence the horizontal. Now, because it affects the horizontal before something's being done to it, and you know that the X and Y has inverse relationships, right? When you express X in terms of Y, Y versus X, that's how you define inverses, right? And that's kind of if you sort of think about that, right? That's the reason why when it's a minus sign, it moves to the right. When it's positive sign, it moves to the left. When B is bigger than 1, it actually shrinks horizontally. In some functions, it looks like it's actually increasing vertically, and so on and so forth, right? Anyways, so we're going to be doing the quadratic function where hk, that's right here, oopsie. Let's go with blue, right? That hk right there is actually a vertex, right? And then we are basically moving around the parent function, right? Yeah. Anyways, so why don't you go ahead and take your time and describe the role of each based on the A value here, right? Whether it's absolute value is greater than less than 1, when it's less, if it's negative, what happens? And the K value over here. And why don't you go ahead and fill out what you think you know, right? And then I'll confirm that if it's correct. All right. And draw the picture, do it in pencil. All right. Pause the video, guys. All right. So here is it. Okay. I hope you got it right. So A's, all the A's and K's are vertical. And then clearly there's a typo here. This is oh, I just realized this. This is obviously horizontal. Oopsie. These two are both, it's not writing, horizontal, right? For both of them. If it's greater than 1, it's actually a compression. If it's absolute values less than 1, meaning it's between 0 to 1, where B is positive, it's a stretch by a factor of B. Okie doke. All right. And we got the reflections over here. All right. Yeah. I mean, that's why especially with the parabolas, right? We had this rule where if A is greater than 0, we would open up. And then if A is less than 0, we're open down, right? And in terms of the horizontal reflection, because the left and right is symmetrical, if you flip it this way, it really doesn't look any different, right? And we got the horizontal translations, okay? And the vertical translations. All right, guys. And here's what the graph looks like, right? With it, I hope you had that correct. So this is actually more the same, right, as we've done in the past. So once again, these are horizontal. Oopsie. Horizontal. For that right there. Okay. And the key thing over here is that I think what trips up some people, right, is that when A, yeah, the book used A, it should be B, but if it's bigger, it actually went this way, didn't it? It actually shrank, right? It's a compression. However, this is a big however, right? If you expand this out, it's a b squared. So the effect of the b is that if you have a number in the front, let's say 2, if you square that, it actually becomes 4x squared. So horizontal compression by 2 is equivalent to it having vertical compression of, it's going to look exactly the same, right? But it's not the look that we're concerned about, it's how we got there, because this is unique to, let's say, uh, parabola, right? But it's not going to be the same. It's not going to look like it looks about the same as the vertical stretch when it comes to, let's say, graphing of the sine and cosine or tangent, right? So this right here is a function dependent, right? So don't conflate the two. It's only unique to certain functions, and one of them happens to where the horizontal compression and stretch have similar counterpart to this, and that relationship is I just showed you right here. Okay, sounds good. All right, guys, and that's let me make it a little bit smaller. Right, make sure you take a good note and make the right connections. Right. All right, guys. So why don't we do this? Why don't you guys go ahead and do the self-assessments? And there are a total of 7 questions, right? Yeah, 7. You know, um, at this being the honors class, I mean, no more than 1 minute per question, right? So it's usually a minute or less. Stop the videos, guys. Actually, I won't show the answer key. I did that in the classroom. So let's move on to um the actual lesson part. Okay, here we go. So we're going to be talking about the transformation of the quadratic function, right? The lowest point of parabola that opens up, right? And then there's a highest point on a parabola that opens down. It's called vertex, right? So if A, see, if the A is positive, it opens up this way. The vertex is actually the lowest part. And if A is less than 0, it opens down like this, right? So vertex is the maximum value. Yeah, there's actually a lesson right behind this that talks about maximum min as if something new, but you could clearly see that that's what it is, right? But the key thing about this part is that when you're written in a vertex form, I should underline this, right? This is called a vertex form, which is in that format right here, right? H represents the horizontal translation, and K represents the vertical translation. But in reality, what that really means, right, is that let's say you have this right here. That's a 0, 0, right? If you switch by H and you go by K, you're essentially creating this right here, HK. As far as I'm concerned, I like to think of that as a new origin. In the past, I used to call it NPR. Uh, you know, new point of reference. But yeah, or you could just say new origin, right? So if you think of it that way, and then once you shift everything, you treat this part right here as now the reference point, and then you draw the x squared. If you have the a, you would draw ax squared right there. Okie dokie. And then a here indicates the vertical stretch, or I don't know what this book keeps says shrink, right? A respectable publication should not be using word shrink. It's a compression. Okay, that's something that I would say to the class to sound a little bit more hip, right? Anyways, here it is. And then we have example over here. This is something that you should be able to do. So is this continuation from the previous chapter? So why don't you go ahead and pause the video to see if you got this. Okay. All right, here it is. Well, the G is the vertical stretch by a factor of 3. And then there's additional translation, unit by translation down by 3, right? So if you have a function f, it's a vertical stretch is you put on the outside over here, right? So this is actually vertical stretch is the A and that's the K, right? So that's exactly the way we put it. Because remember, g of x is A times f of b of x minus h plus k. I still prefer C and a D. As for a general function, right? But if it's a parabola or absolute value, then HK, because it's a vertex, makes sense. But other functions, right? We don't call it HK the vertex. It's a new point of reference, right? Well, anyways, so clearly there's nothing here that's horizontal. So they're either the default value for A and B is 1, and the default value for H and K is 0, 0, right? So that means that it's a 3f of x minus 3. But what is f of x? Substitute it in there. It's x squared. So g of x, therefore, oops, what I should have said, therefore, the g of x is 3x squared minus 3. Okay? But if you look at this right here, that's like having x minus 0 squared. So that is the h, that's the k. So the hk is 0, negative 3. Okie dokie. All right, guys, let's go to example 2. Let the graph of G be a translation of 4 units left and 2 units down. Uh-oh. So this left, that's H. And down, that's a K. This HK, isn't it? Why don't you guys go ahead and pause the video and see if you could get this done. All right, here it is. So the fact that it's a translation right here makes it, because it's a left, is plus 4. Because remember, with horizontals, it's opposite of what you think it is, right? It's opposite of how it affects the verticals, right? 2 units down is negative 2. But there's one thing that I forgot to mention, right, just a few seconds earlier, is that there's a reflection. It should say over, really. Reflection over x-axis, meaning if you have something like this, it becomes like this. So the b is negative 1, right? So you put negative 1 over here. Now, if that sort of confuses you, right, this is what you should think. If it's a negative 4, 2 down, the position is over here, right? That should be negative 4, negative 2. If you flip it, it becomes what? 4, negative 2. So once you flip it, the HK should be 4, negative 2. If you look at this is exactly what that is, right? The reason why you could say that is because you're going to be squaring it and it has that effect. Okay, let's move on. Well, anyways, so once you do that over here, you know that this has to be input of the function, and the function is x squared minus 5x, right? And you plug it in. Instead of the x, you replace it with the x negative x plus 4. You expand it out and combine them. It turns out to be g of x is x squared minus 3x minus 6. Okie dokie. And if you'd like to confirm this, then what you should do is go to the Desmos, graph this, right? And then do this part, right? And then do this part separately to see that indeed this g of x is the reflection. Like if you pretend the y of x is like paper, folded paper, the fold in a paper, just flip it. If they match, then it's a symmetric uh, about y-axis, right? All right, guys, let's keep moving. Example 3. Let's see if you could do this on your own, right? Oh, pause the video, right? All right, guys, here we go. It looks something like this. So all I did that's my y-intercept is 25, right? And then that thing right here, because it's negative, it's going to go like this. Boom, right? And I even know where this highest point is. How do I know that? Because that value right there is where negative b over 2a is, which is 1 divided by twice the negative 0.03, right? So you can sort of figure that out. Well, anyways, right? Um, but that's not what they're looking for, so we're not concerned about it, right? So what they're asking you to do here is the crew wants to raise the ladder so that it goes 10 feet further. Oh, I don't know what that is for now. We could find it. We'll go 10 feet further. So whatever this is whatever it is plus 10. And if I know what the distance over here is, I could just raise that much and that right there will hit. Is that sort of making sense? Yeah. So more important than the procedure is that you need to sort of figure out stuff like that on your own, right? So read the question and think about it. So the first thing I did was I set the h of x equal to 0 because I was kind of curious where this will hit the ground, where the water would hit the ground, right? And as it turned out, I decided to use quadratic formula, and I always prefer to find the determinant right away, right? Sorry, discriminant right away. I don't know why I always say that, interchange those two. Discriminant, by doing it, it just makes it easier, right? As it turns out, it's much, 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 much simpler, simply because, look, this is 4 times 25 right here, right? 4 times 25 is 100, which makes this 3. So this 1 plus 3, which is 4. Okay. Anyways, when you go through the calculation, the x on the left-hand side is negative 16 2/3. This right here turns out to be a 50, right? So that's a 50 right there. Oh, so we want to hit it 10 feet further, which is 60, right? And we could do that by knowing how far that down is. So now I'm kind of curious what the value is when it's 60. So all I did was this right here, guys. Boom. So what is the h of 60? When you go through the calculation, it's minus 23. So I want that to be 0, right? So we need to raise it by 23. So what do? We are adding 23 to the function. Yeah? There you go. So g of x is h of x plus 23. And therefore, the g of x is negative 0.03x squared plus x plus 48, right? Um, yeah. And I think that is it for me. All right, guys. All right. I shall see you again. Let me just make that like this in the next class. All right. So that was lesson on transformation of quadratic functions. I'll see you next class.